Okay, we're at the end. The last section of chapter 9, the last section of the semester. So we're still in chapter 9 again, 9C, on modeling our world. Now, this section is on exponential modeling, and just like I mentioned at the beginning of 9B, I reminded you that linear model, that linear growth, as we covered in 8A, a function grows linearly if it increases at a constant by a constant amount. You keep adding the same amount to the quantity over and over and over, whereas exponential growth is something that increases by a constant rate. We're just going to jump right in with the equations, the first of the equations. So an exponential function grows or decays by the same relative amount. That's what I was just saying about how exponential growth works. Okay, so for any quantity q growing exponentially with a fractional growth rate r, we have this equation. All right. Now, this explains what all those variables mean, but I want to point out first of all that q, this is in this function, this is the dependent variable, and t, this is the independent variable. So when we start talking about plotting points with this function, it's going to be of the form of t comma q, where t is generally speaking a time, q is the quantity that is growing or decaying. Okay, like I said, q is the value, the current value of the exponentially growing quantity at time t. Q0 is the initial value. It's how much you start with at time t equals 0. R is the fractional growth rate. Now, generally speaking, R will be given as a percent, something like, I'm just going to make up a number, like 3.2%. And before you can use that, always remember we need to convert percents into decimals. So that would be 0.032. So you want to convert that to decimal before you plug it in anywhere. And t is time. Now, if r happens to be negative, that means we have exponential decay rather than exponential growth. And the units used for t and r have to be the same. That is, I wouldn't want to have, t measured in years and the growth rate measured in months. You want to have them in the same units. So in this example, we're going to use the fact that in 2010, the census found the U.S. to have a population of about 309 million people with an estimated growth rate of 0.9%. So we're going to write an equation for the U.S. population that assumes exponential growth at this rate. And then on the next slide, we're going to use that equation to predict the U.S. population in the year 2100. All right, so the equation we have is that Q equals Q sub 0 times 1 plus r to the power t. Well, we're told that in 2010, which is what we'll assume t equals 0, so t equals 0 will be the year 2010, that the population was 309 million. That tells us that Q0 is 309 million. We're also given the rate, the growth rate. R is equal to 0.9%, which we need to write that as a decimal, so 0.009. And now it's just a matter of just plugging into the equation. So Q, the equation that we want, Q equals 309 million times 1 plus 0.009 to the power t. And simplifying that just a touch, Q is going to be 309 million times 1.009 to the power t. And on the next slide, we'll answer the other question about using this equation, this mathematical model, to make a prediction. Now, if the year that we want to calculate is 2100, okay, and the one we started was 2010, that tells us how to figure out what t is. T is going to be 90 because 2100 is 90 years. after the year 2010. And so our exponential function, which recall was q equals 309 million times 1.009 raised to the power of t, that was our exponential function that we calculated. We're just going to plug 90 in for t because it's 90 years later. And that's going to be about 692 million. And that's the answer. That's what the population will be in the year 2100, according to this model. So now let's talk about how we can graph exponential functions. And we use something called either the doubling time or the half time, depending on whether the function is increasing or decreasing. So we use points corresponding to several doubling times, or if it's a decay, half-lives, using the point 0, q0 as the first point we plot, because that's at t equals 0. Now, for an exponentially growing quantity, then 2 times q0 is double the initial amount, and that's how much is going to be there after one doubling time, right? Which we denote by t double. And then if we double from 2 times q0, double that to get 4 times q0, well, that's going to be after 2 doubling times. If we double that again and go from 4q0 to 8q0, well, that's after 3 doubling times, or 3 times t double, and so on and so forth. And those are the points we'll plot to see what the graph of an exponentially growing function looks like. If we have a decaying one, then we go from q to q half at t half, the half-life, and then that goes from q0 over 2 to q0 over 4 after 2 half-lives, because we divide by 2. Divide q0 over 4 by 2 to get q0 over 8. That's after 3 half-lives, and so on and so forth. And we plot those points to get the points we would graph for an exponentially decaying function. So here we have the graph of an exponentially growing function, and we'll plot all those points we talked about before. So when t is equal to 0, there's q0, and then that doubles to 2 times q0 after one doubling time. And so the graph looks like this. Then it doubles again to get to 4q0. That's after another doubling time, 2t double. And then we get that point. Then after another doubling time, it's going to go from 4q0 to 8q0, and then we get the whole graph. That's an exponentially growing function. Similarly, if we have an exponentially decaying function, that is a function that's getting smaller, at time equals 0, we have q0, the initial amount, that halves to 1/2 q0 after 1 half-life, and we get this point. And so the graph looks like this. But then it halves again to get 1/4 q0 after another half-life, and we get that point. Halves again after another half-life, and we get that point. So this is what the graph of an exponentially decaying function looks like. So here we have 3 different equations that we will use to model exponential functions. Now, depending on what information you're given, that's the equation you use. For example, if you're given r, if you're given the rate of growth or decay, then you use this equation, the first one we talked about, right? And if you are given, in the wording of the problem, if you're given r, that's what you'll use, all right? However, if you're given the doubling time, if the problem says the doubling time of this quantity is a certain number, then you use the second equation that has the t double in the equation. You always look to see what's in the equation, the information you have. If you're given a half-life, then you'll use this equation. You'll use the one that has the half-life in it. So again, depending on what information you're given, if you're given the rate, you use the first one. If you're given the doubling time, use the second one. If you're given the half-life, you use the third one. You don't have to memorize any of these. If this type of problem shows up on the final exam, I will give you the equations. You'll have to know how to pick out which one to use. All right, for this example, we're going to be talking about the country of China's coal consumption. So the past several decades, China has experienced rapid economic development, which means it needs more energy. As a matter of fact, its energy use has been growing exponentially. And now China generates more than 2/3 of its energy by burning coal. During the period from 2000 to 2012, China's coal consumption increased at an average of 8% per year. And the 2012 consumption was about 3.8 billion tons of coal. What we want to do is use these data to predict China's coal consumption in the year 2020. And I realize that, if you're watching this video when I recorded this, it is the year 2020. What a year it's been. But the textbook here was written about 5 or 6 years ago. So that's why it's referencing 2020. But I also want you to know that 2020, before we can have an accurate measure of this, we would need to have some time pass. So we couldn't just really look up China's coal consumption right now or even next year to see if this model is accurate. We would need a few more years to check it. So with that said, let's go ahead and see if we can work this problem. Notice that we are given the rate. We're given the rate, which tells us that we'll use this equation. Q equals Q sub 0 times 1 plus R to the power of T. Now, we're also told that in 2012, this was the coal consumption. So that means T equals 0 is going to be in the year 2012, and that Q0 is equal to 3.8 billion tons of coal. 3.8 billion tons of coal. This is enough for us to write the equation. The equation will be Q equals Q0 times, I need the rate. The rate R is equal to 8%, which writing that as a decimal is 0.08. So going back to the equation we're looking for, Q is going to be equal to our initial value, which is 3.8 billion. So 3.8, 1 plus 0.08 to the power of T. That is Q is equal to 3.8 times 1.08 to the power of T. And then to answer this question, what would we predict the coal consumption to be in the year 2020? Well, since we know that we decided that T equals 0 was the year 2012, that means T equals 8 is going to be the year 2020. So we just plug 8 in for T into this equation. So it's going to be Q equals 3.8 times 1.08 to the power of 8, which works out to be about 7.0, and that'll be 7.0 billion tons of coal. So according to this mathematical model in the year 2020, China is using about 7 billion tons of coal. So it turns out this isn't going to be a realistic model. This is what the model would look like if we extended it on, starting with, Q equals T equals 0, and they use a given amount of coal, and it goes up to that much after one doubling time, and it keeps increasing and increasing and increasing. So by the year 2057, they would be using 121.6 billion tons of coal. That's not realistic. China has some serious problems when it comes to pollution from coal burning. A lot of regions in China have really, really bad pollution, and they have waste and things like that going on. So they're probably not going to keep burning coal like this. They're going to switch to cleaner energy sources like gas or renewable sources. They're not going to, probably the graph is more likely going to go something like that. It's going to taper off after several years. It's not going to keep going exponentially as far as coal consumption goes. Because it's just bad for China as a country. So they'll probably start tapering off. It's unlikely, because of global warming and pollution issues, they would continue using that much coal in the long term. This example, we are talking about drug metabolism. So if any of you are nurses, this will be especially relevant to you. All right, so anytime you put something into your body, any type of drug, whether it's antibiotic or a vitamin or another type of substance that has a half-life. Alcohol has a half-life. Marijuana has a half-life. I saw people, they're being drug tested or something. They want to have a certain amount of time pass, so it's not going to be in their body anymore. So antibiotics suppose there is an antibiotic with a half-life of 12 hours. So if you had something that you knew had a half-life of 12 hours and you took 100 milligrams of it, all right, in 12 hours, there would be 50 milligrams left. In 12 more hours, there would be 25 milligrams left. In 12 more hours, there would be 12 and a half milligrams left, and so on and so forth. That's how half-lives work. So in this example, we're going to suppose that there is an antibiotic that has a half-life of 12 hours. Now, by the way, we immediately will note that since this problem is talking about half-lives, we know that we're going to be using this equation. Q equals Q sub 0 times 1/2 to the power of T over T half, because we're using half-lives. So finishing the problem. A 10 milligram injection of the antibiotic is given at 1 p.m. How much of it remains at 9 p.m.? So we're going to answer this question, and then we'll draw a graph on the next slide. Before we can do the mathematical model, let's fill in the numbers. The initial amount given is 10 milligrams. That's Q0. And the half-life is we're told the half-life is 12 hours. So that means the mathematical model, that is the equation, is Q equals 10 times 1/2 to the power of T divided by 12. So now we can answer the question. How much remains at 9 p.m.? Well, T equals 0. That is at 1 p.m. That's when it's injected, right? And so that means T equals 8 is going to be at 9 p.m. That is 8 hours later. So Q is going to be, the amount at 9 p.m. is going to be 10 times 1/2 to the power of 8 over 12. That's 10 times 1/2 to the power 2/3, which if you use your calculator, that works out to be about 6.3 milligrams. So at 9 p.m., there is 6.3 milligrams remaining in the body. So as we said, 8 hours after the injection, there'll be 6.3 milligrams of the antibiotic remaining in the bloodstream, 6.3 milligrams. Now, if this is graphed like this, starting out with 10, then it goes down to 5 after 1 half-life, goes from 10 to 5 after 1 half-life after 12 hours, and then it keeps decaying to 2.5, and then half of that getting smaller and smaller and smaller, steadily decreasing steadily towards 0. Now, it's never going to get to 0 because of the way the function works. However, eventually the amount will be so small that you won't be able to detect it anymore. And just summing everything up about rates of change, as we saw in the last section, linear functions have straight line graphs and constant rates of change. Exponential functions have graphs that rise or fall steeply and variable rates of change. So here we have an exponentially growing function. The blue one is the exponential function. And then we have at different points what the corresponding linear function would look like. If we pick a different point, the linear function would look like that, and it gets less and less steep as you go to the left. But at every point, the exponential function is always growing faster than linear. On the right, we have an exponentially decaying function, that blue one, that goes down like that. And at each point there, we have what the corresponding linear functions would look like. In every case, it's going to be not quite as extreme as the exponentially decaying function. So this is it. This is the last section of the last chapter. If you have any questions on anything, as always, please let me know, and I can answer them via email like I've been doing, or we can meet, or whatever you need. Work through the homework, the quiz, and the final exam material has already been uploaded. Please work through all that, and I will talk to everybody later.